I will start with the very first case, which is the self-weight. So let's look at self-weight. Before we write anything down, let's observe this. So the self-weight actually acts along the entire length of what's called a rafter or the roof structure, and then that is acting towards the center of the earth. So all these angles, all these arrows are vertical. So note that this is very different from what we have done before. Before, when we saw evenly distributed forces, they were always perpendicular. The force arrows were always perpendicular to the actual beam. And in this case, we are actually not directly dealing with the beam, we're dealing with this rafter, and these force arrows are not directly perpendicular to this. So let's begin to write down some notes here. So first of all, this is self-weight. And in this particular case, for educational reasons, we'll just make it 500 Newton per meter. But please note that this is 500 newtons per meter along this beam and not along this horizontal direction, which could be misleading if you just look at these arrows. And to make our life easy, we have the symmetry 500 Newton per meter also on the other side. And what does that mean? So when do we have these cases? Again, 500 Newton per meter is probably not a very realistic way, but it gets the educational point across. So in reality, this can be much heavier based on the weight of the shingles, for example. Or it could also be the rafters themselves, or insulation panels, just like electrical components, the ductwork, and then also the drywall that's usually hung, or OSB components. So pretty much anything that can cause a load on the roof system. So let's keep in mind that these forces are all identical in the sense that they all act towards the center of Earth. And that they all effectively act along the length of the member. And that takes us back to the structure. So let's take a look at the structure. What do I mean by the member? So we have the member here from node A to node C, and we have the same or similar member from B to C. And so it acts along this line. And now, similar to the frame that we discussed in the last lecture, that was an orthogonal frame, we had a hinge somewhere in the frame. And now we have a hinge at the peak of, or the top of the roof, if you will. And we, of course, therefore must have two pins at A and at B. And so we now need to discuss the support reactions, because before we can analyze any internal forces, we always need to look at the support reactions. And you know from the previous lecture that we effectively have two support reactions. Let's call this here RAY and RBY. And we also must have RAX and RBX. And so it is very common initially to overlook the X components. The vertical is clear because everything that goes up has to come down. So these two balance pretty much everything that comes down. But because of the hinge here, if these were rollers, you can probably imagine that they would just slide out. And therefore we need something to prevent that. So we need RBX and RAX. But what's important for us here, for the first non-orthogonal frame that we look at, is that it's also a symmetric system. And in fact, it's a very easy symmetric system because it has a length or triangle of 3, 4, and 5. So the length along that beam is actually 5 meters, right? So we have 5 meters here. And so we can actually say that we have a symmetric system. And because we have a symmetric system, we know that RAY must be equal to RBY. So that is one condition that we can take from the symmetry. And similarly, we can say that RAX is equal to RBX. So that must be true because otherwise symmetry would not work out. So how much is RAY? That's the easier one to start with. So RAY is pretty much a half of all the vertical loads that come down. Or RAY plus RBY is equal to all the vertical loads. So I can write down here that it is effectively 1/2 times all the self-weight. How much self-weight do I have? I have the 500 Newton per meter over this length of 5 meters, and I have that effectively 2 times. So 1/2 times 2 times 500 Newton per meter multiplied by 5 meters. And so that is exactly how much load we will have, and that is 2.5 kilonewton, or 2,500 Newton, which is equal to 2.5 kilonewton. So that is a good start because now I know that this one here is 2.5 kilonewton and RBY is also 2.5 kilonewton. But the question now is, how much is RAX and RBX? And if we remember from last class or from our last lecture, when we have systems like these, frames with like a hinge in the middle, or anywhere for that matter, we can always take the sum of the moments about that point and use the condition that the moment is equal to 0 at that hinge. And so therefore I can just take half the system and rotate about C. So I'm going to take the left side here, RAX, which has a lever arm of 4 meters about that point. RAY has a lever arm of 3 meters. And this force here is concentrated in the middle of the 5 meters, but because it's acting perfectly vertical, it has a lever arm of 3/2. But I will write that down for you now. So to calculate RAX, I have to take the sum of the moments about the hinge at C and set it equal to 0. And of course counterclockwise positive. And so I start with my unknown. 0 is equal to RAX multiplied by the lever arm of 4 meters, because that's the shortest distance between that point and the line of action of RAX. So times 4 meters. And the rotation of that RAX that I assume happens to be counterclockwise, therefore that is positive rotation. Then it's also RAY, but I already know that's 2.5 kilonewton. So 2.5 kilonewton multiplied by 3 meters in this case. That's the vertical lever arm. So just to be clear, that's this force about this point with that lever arm. And that rotates actually clockwise, so therefore that is negative. And last but not least, I have to include the 500 Newton, so that's 0.5 kilonewton per meter multiplied by 5 meters. And now careful with the lever arm, because the resultant effectively is acting in the middle and it's vertical, so therefore the distance is 1.5 meters. So 1.5 meters, or 3/2, and that is rotating counterclockwise about C, so therefore that is a positive lever arm, if you will. And if I now rearrange all this, then I will end up with this equation down here. And the answer then is 0.9375 kilonewton. And this is not for significant figures, but just to carry our understanding through. It's easier to use these numbers here for this educational example so that later on we can clearly identify which number belongs where. And due to symmetry, Rax, remember, is also equal to Rbx. And now I solved my support reactions. And in fact, I'm going to include that here in my system. So that is 0.9375 kilonewton. And the same is true here, 0.9375 kilonewton. And so I now calculated my support reactions for self-weight of a non-rectangular frame. And that is the first step towards calculating internal forces. Now let's move on to the next issue, and that is if you calculate internal forces, you need to find the forces that are actually 100% parallel to the member. For the normal forces, it's parallel, and for the shear forces, it's perpendicular. The problem that we currently have is that the support reactions are not. And so what we have to do next is actually break down the support reactions. So our next step is to do the breakdown of these support reactions. And you can already see in the picture here that's already been done, at least conceptually. So let me point towards it. So Rax, which we just calculated, has a component that is perpendicular to the beam, and it has a component that is parallel to the beam. So I'm going to call these Rax parallel and Rax perpendicular. And similarly, Ray parallel and Ray perpendicular. So maybe the first step I should do is bring down my actual results here. And so I had Ray being equal to 2.5 and Rax was equal to 0.9375. All right. Now we need to understand how to break them down. And so to do that, I look at my general triangle. Remember, it's a 3, 4, 5 triangle. And so we're going to use this information, the 3, 4, 5 triangle now. I need to pretty much connect which side is which. So let me zoom in first into my standard triangle here. So this I know for sure. And I'm going to call this angle here alpha. And the way I think of this is that alpha connects the 5 and the 3 side. And alpha has nothing to do with the 4 side. So I now have to bring that into my other two triangles. And the easier one to see is probably the one for Rax. So let's look at Rax here. Rax is horizontal, and Rax parallel is parallel to the member. So that means that the alpha angle must be situated right here, right? And now the next thing I know is that Rax is the hypotenuse, which is the 5 side, and 5 is connected through alpha with the side that has a length of 3 here. So I know that I have 5 here, 3 here, and by default that makes this the side that is 4. And similarly, I can do something for Ray, but the way that's easiest for me to see actually is if I extend my line that's parallel. So if I have a line that's parallel here, and then I have a horizontal line, then I get easily my alpha again. So here I have alpha, and that alpha has, that triangle that I just drew has a 90-degree angle, and so that turns this into, let's call it beta. And therefore, this angle here must be alpha again, right? Because we have the right angle right here. And now I can use the same logic again. I can say, hey, RAY is the side that has 5 long, and alpha connects 5 and 3. So RAY perpendicular is the 3 side, and RAY parallel is the side that has a length of 4. So now I identified my 3, 4, 5 triangles, and now it is actually easy to break down my support reactions. So let's do that. Let's first calculate RAX parallel. And RAX parallel is equal to RAX multiplied by 3 divided by 5, right? So that is here RAX needs to be divided by 5 and multiplied by 3. And so that way I get RAX parallel. To no surprise, it's the quite opposite for RAX perpendicular. So therefore I have RAX times 4 divided by 5. And I can now calculate my final results here. I have to plug in RAX, which is 0.9375. And so I get 0.5625. And I get 0.75. And both of those are in kilonewton. And let's now focus on the triangle down here. So I have RAY, and to calculate the perpendicular part, I have to use 3, and to calculate the parallel part, I have to use 4. So in numbers, that looks as follows. RAY parallel is equal to RAY and multiplied by 4 divided by 5. So that's this component here, the 4 and the 5, and the parallel component is this one. And my RAY perpendicular must be the opposite, of course, RAY multiplied by 3 divided by 5. And so if I solve these, I get effectively 2 kilonewton for the parallel component, and I get 1.5 kilonewton for the perpendicular component. So let me repeat what we've just done. We took the support reactions, the ones that are vertical and horizontal, in a global coordinate system, and broke them down into parallel and perpendicular components. So here's the perpendicular components. In fact, in this picture, the perpendicular components are red and the parallel components are blue. And to do that effectively, I had to use the 3, 4, 5 triangle that tells me exactly how the geometry of the system is arranged. So now you probably see what the issue will be here. We broke it down, but we probably also want to combine them. So for example, the perpendicular components are opposing each other, and I want to know how much there is either, away from the node or towards the node in the combined version of RAX perpendicular and RAY perpendicular, and then quite the opposite for RAX parallel and RAY parallel. They both are added together. They both push on the node in the direction of the member. So we now have to bring them together, and we will do that on the next page. So here on the right side, we have that very picture, except that now we only have one parallel component and one perpendicular component. So what I have to do now is I effectively have to collect all my components. And let's do that together. So I need to identify RA parallel. So now that y and x is gone, I'm only looking at RA parallel, and I do that by RA y parallel plus RA x parallel. And if you run the numbers for that, you will end up with 2.5625 kilonewton. Similar for RA perpendicular, except that now they're actually subtractive. So I have RA y perpendicular minus RA x perpendicular. And that is because they were acting opposite to each other. So one of them forces the other one to lose some intensity, if you will. However, they actually turn out to be 0.75 kilonewton. So that is all nice, except let's keep in mind that self-weight also has components that are parallel and that are perpendicular. So we now have to also break those down, and what we effectively will be doing is we will have a vertical force that of course is the hypotenuse, which is 5. Then we have a parallel component, so this is, let's call it F parallel. And then we have a perpendicular component, so this is F perpendicular. And so we need to once again connect our 3, 4, 5 triangle there, but that has already been done down here. So we already know that this is the hypotenuse with 5, and then 4 and 3 is already given with the same logic. So now what I can do next is I can actually calculate my internal forces, or better yet, I can create my functions for the normal force, for the shear force, and later on for the bending moment. So let's look at it for the normal force and shear force. Before I do that, I think it's smart to use my numerical values here and add them. So RAY parallel is 2.2625 and RA perpendicular is 0.75. So let's look at our normal force. So as always, and as we have done before many times, we're just going to set the sum of the forces and x is equal to 0. Just be careful with the x, because x now runs along the dashed fiber. In fact, that's what the dashed fiber always says, that we have to go x positive from the left to the right if the reference fiber is on the bottom. And so I can now set that equal to 0, and I already brought in here my normal forces, or like all my internal forces actually, but I start with my normal force. So it's positive n of x plus 2.5625, that's this guy. And now I have to be careful because I'm missing how much this component from the normal force is, so the 4 part of the triangle. And how do I do that now? I guess it's easiest to have the 500 Newton per meter multiplied by x meters, because keep in mind that x is running in this direction. So this is where x is running now. So x meters, but I also have to account for the part that is only parallel to the member. So what I have to do is divide it by 5 and multiply it by 4. So I'm going to do that now. So multiply by 4 and divide by 5. Last but not least, I have to decide if it's positive or negative. And since my n here is positive to the right, this one is opposing it. and therefore it has to be negative. So now I'm going to have a negative 500x times 4/5. And if I solve this now, I probably would do better to turn this into kilonewton. So this here would be 0.5 kilonewton per meter. And now I can combine the units, and I will find that I end up with 0.4x minus 2.5625. And of course the whole thing is in kilonewton. And now I created a function for the normal force along the member A to C. And remember that this beam here had a length of 5 meters. So the minimum value I can plug in for x here is 0. And the maximum value I can plug in for x is equal to 5 meters. Also, notice that when I plug in 0 for x, that then I will find the support reaction here, or the parallel component, which that must be true too. So if I plug in 0 here, then that is true. I actually get a compression force of 2.2625. So that matches. So with that said, it's probably easy for us now to use the logic for the shear force. So let's look at the shear force. Once again, I set my equation, sum of the forces in the y direction equal to 0. Y in this case is y as it is defined by the dashed fiber. So now my shear force is actually going down, which is negative, but positive defined shear force. I have 0.75 going up, so therefore that's positive. But I have this component from the 500 Newton per meter going down. Therefore it is negative 500 or 0.5 kilonewton per meter. And that is multiplied by x meters. But once again, I need to break it down to the 3/5 component, so times 3/5. And if I solve this now, I will find that it's negative 0.3x plus 0.75. And that is in kilonewton. Once again, I can run x from 0 to 5. And if I plug in 0, I need to find 0.75, which is the case here. So that concludes the shear force. And I think we're on a good track here. So let's move on to the bending moment, which is similar to the shear force, except that now we need to consider the lever arm, right? So this force actually now gets a lever arm, which will become tricky. The lever arm for the 0.75 will be easy. So what I will do now, and I need you to understand this, that we're actually taking the sum of the moments about this point, which now is of course running in terms of x. So let's look at that. So my sum of the moments is equal to 0, counterclockwise positive. And my defined moment here is already counterclockwise, therefore positive, positive. And now I have the 0.75 here that is turning about this point. So the perpendicular force here, so this is times x, 0.7. So I need that to be 0.75 kilonewton times x meters. All right. So I have that component covered, and now I have also to include the 0.5 kilonewton per meter times x. So that would be 0.5 kilonewton times x. X is along this direction. And now I have to be careful because I need to account for the lever arm, which is pretty much half the distance along here. But keep in mind that this 3 now needs to be expressed in terms of x, because x technically grows in this direction, and as x grows, the component in the horizontal direction also grows. And so what I will have to do is express this horizontal component in terms of x. And the way I do that is by, of course, my ratio, so times 3 over 5x. But it's only 1/2 of that, right? Because it's the lever arm. So that is effectively the lever arm. And you see that now x is squared in that equation, right? So I have x here, and therefore it's a squared equation, which is good because we know that the moment must be parabolic. So ultimately, it's minus 0.15 x squared plus 0.75 x. And this equation, of course, must be in kilonewton meters. And there you have it. So number one, if I plug in 0 into this equation, then my value has to be 0 because there's a hinge here. I mean, this is only a hint that I give my students, but ultimately there's just a support there. And so the support reactions have no lever arm yet. Therefore, if you plug 0 in, the moment must be 0 at this location. And that is true if I plug this in. Also, what's true is that this equation, the shear force, is the derivative of the moment. And what have I done now? I have on this page effectively my internal forces. And in fact, I don't just have the internal forces, I also have functions for the internal forces for my roof structure. Be careful, it's only for the left side of the roof structure, but with like deep thinking, it's probably easy to also extend the knowledge to the right side. Just don't do it blindly because the right side obviously is similar, but also with a few tricks. But we will cover that now on the next page. So now I have my diagrams here for each of the load cases, or I guess for each of the force cases, I should say. So let's start by identifying that. So let's start with the normal force, of course in kilonewton. Then we have the shear force, also in kilonewton. And we have the moment in kilonewton meters. All right, and now I remember my equations. So let's start with the normal force up here. My equation, I'm just going to bring that over from my previous page. So that was 0.4x minus 2.5625. And of course, again, kilonewton. So now how do I bring that over into my diagram? So again, here, if I plug in 0, I will actually end up with negative 2.5 something. So what is a negative again? A negative means the side of the dashed fiber or the reference fiber, and it's actually going to be down here. Notice that this here is a right angle. I will not show this in the future again, but that's like important to understand. It's not like a line's random, it's actually perpendicular to that. And so now I can actually plug in values to my equation here. So I can plug in 1, 2, 3, 4, 5 until I convince myself, or I can understand that there's load pushing here, there's more load pushing here, more load pushing here, more and more and more and more. And so therefore the normal force, the compression, gets more towards the bottom of the rafter. And therefore I have to actually have a slope that decreases towards the top, if you will. So it goes from here to less internal force. And so all I need to do is plug in 5 and then connect my values. If I plug in 5 there, I will end up with a slight value on the top, right? Because the top is a little bit in compression from the other part. So it looks something like this. And in fact, if I plug that in, I end up with a value of minus 0.5625. And now I can connect my dots, if you will. And it makes hopefully perfectly sense that the compression gets more and more as you walk, as you come to the bottom of the rafter, if you will. And now we see that it's actually in compression, and the compression is increasing. And that is towards the bottom of the roof. And notice that it is not 0 at the top, which is actually due to the pitch or the angle of the roof, right? So depending on how it's pitched, the right side pushes on the left side and the left side pushes on the right side. In fact, since we understand that the left side pushes on the right side and the right side pushes on the left side, we are probably able to draw the diagram for the right part now, which is very similar, and you hopefully understand that it is also in compression, so therefore it must be negative on that side. And then it is also negative up here on the top. And then I can connect the dots again. And close my diagram, which now looks like this. And I know that here on the top it's also negative 0.5625. And by the way, on the bottom here and here, it's both minus 2.5625. And now I completed my normal force diagram. Let me highlight again what's important to understand for these diagrams is that these lines on the top and on the bottom are actually perpendicular to the axis of the beam. And I must have higher compression on the bottom than I have on the top because the weight increases towards the bottom, right? So there's like more and more accumulating that's pushing down on the foot of the roof. And here on the top, it's not 0 because the left side pushes on the right side and the right side pushes on the left side. So there's a pre-compression, if you will. And that concludes our normal force diagram. We can do the very same thing now for our shear force diagram. So let's bring over our equation first. It will make our life easier. So V of x was equal to minus 0.3 x plus 0.75 kilonewton. So let's start with that. Remember that I started on the bottom left, so I'm going to use that equation, and if I plug in 0, then I end up with positive 0.75. Positive means opposite to the dashed fiber. So I'm going to call this here plus 0.75. And now, if this is the first time I do this and I'm in doubt, I need to ask myself what's happening. And so therefore I just plug in values for x. So for example, 1, 2, 3, 4, 5, of course with a maximum of 5. But if I plug in 5, I actually end up with negative 0.75. And so that's the value I'm going to use here to draw my diagram. So that would be something like this. And I know that it's pretty much an evenly distributed force on there, although it's acting differently than what we've seen before, but I know that it must be linear therefore. And so I have a positive area here, and I have the negative components here. And if you paid attention, you see it's no different from any beam that had like self-weight on it before. Now let's think about how we can apply this to the right side of the system. So please note that the system actually is a symmetric system. And remember what we already discovered before, that if the system is symmetric, the shear force system or the shear force diagram is antisymmetric. So and how does it apply now? So instead of starting at a positive value on the foot, I have a negative value. And then here on the top, I have a positive value. And I can connect the dots again. And I get a very similar picture. I didn't do a very good job drawing this here, but the passing through zero would technically happen right in the middle of the rafter. In fact, V is equal at 0 at x equals to 2.5 meters, which I need for my max min moment. So let's look at that now. Let's look at the moment, but not until we haven't reviewed the shear force diagram again. So again, this equation was valid for this member here, A to C. And when I plug in 0 for x, I end up with 0.75. If I plug in 5, then I end up with minus, so I should probably put the value here, minus 0.75. Whereas on the other side, I have 0.75 and minus 0.75. And why is this? Because my dashed fiber remains on the bottom for this component here. And so the system is symmetric. And by the way, the load case is also symmetric. And because that is the case, the shear force diagram must be antisymmetric. And where these pass through 0, which is effectively in the middle of the rafter, that's where we find our min and max moments. And we're going to look at that next. Before I do that, I just want to show you that I bring these center points down effectively. But it's important to understand that now I have a perpendicular line which really defines where things are happening. So this would be perpendicular to the rafter itself. And now I can use my basic knowledge about moment diagrams to help me draw this effectively. The very basic thing and first thing I know is that at each hinge or at the supports, I must have a moment that passes through 0. And now I need to decide, do I want a maximum or a minimum? So in other words, a maximum would be here and a minimum would be down here. And the same is true on the other side, minimum down here, maximum here, or maximum being a positive value, minimum being a negative value. And I also know that it's an even distributed force that was acting on this member and on this member. And so I must have a parabolic function here. Also remember, this is a linear function. This is a linear function in the shear force. Therefore, this must be parabolic, and the same is true here. Last thing now is positive or negative. So effectively, do I draw my arch this way or this way? And the answer is easy. If you remember, the compression on the top, tension on the bottom is a positive moment. That is exactly what we have here, or as we called it in the class, the beam is smiling. So this beam here is literally smiling. It wants to bow down. And because it wants to bow down, the moment is positive. And so I can now easily draw my moment. So my parabola would sit like this, and same on the other side. So there you have the parabolic function with an m max here and I m max here. We will calculate that m max in just a second. But this is positive and this is positive. And of course, this is an x square function and an x square function. And we just have to decide how we calculate that, but it's actually very easy in this case because we already calculated m of x, and m of x was equal to negative 0.15x plus 0.75x, and all I have to do now to calculate my maximum is include like the fact that my shear force passes through 0 at 2.5 meters, so where v equals to 0. And last but not least, we also already talked about the fact that we have positive bending moment. So this is positive bending moment because we have a smiling beam, if you will. So beam is smiling throughout entire lengths. And so you see now that we actually completed all 3 diagrams for a non-rectangular frame with self-weight on it. And once again, the logic is no different. What was challenging here for this problem was to first find the support reactions. And after we find the support reaction, we had to break them down into parallel component and perpendicular component. And then we created these functions, and these functions helped us to really draw the system. Again, for a beginner, it's probably tricky to bring the logic from the left side over to the right side, but that's what practice is for and the homework problems. So here I'm not going to focus on the right side, or like not to explain like how that really works. When in doubt, always make a cut wherever you want to do it, or like create the same function for the other side. It might be a little bit tricky because you want to start from the left side if you create a function here, but the same principles will always work. So, and most important for these diagrams to recap is that the normal force increases towards the bottom, makes sense. Shear force is symmetric, and shear force is anti-symmetric because the system was symmetric, and the moment therefore must be symmetric and also positive because each of these 2 rafters wants to bow down, and therefore it must be positive. So that concludes the analysis for the self-weight on a hinged frame with non-right angled corners. And next up we would be looking at snow loads, which is not very different. We're going to do that separately, but the concept will be the same after some initial massaging of the snow load. So let's do that next.